Okay, good morning students. Today we have lecture number 3 on electromagnetic induction. We have lecture number 3 on electromagnetic induction. So previously we have studied about the electromagnetic induction and we have studied laws of electromagnetic induction. Then we have derived the expression for motional EMF. The motional EMF, that is E is equal to BLV, where E is induced EMF due to the motion of the conductor in a uniform magnetic field, and B is the strength of the magnetic field, L is the length of the conductor, and V is the velocity of the conductor. Okay. So now, the direction of the induced EMF or the direction of the induced current in the motional EMF is given by Fleming's right hand rule. Fleming's right hand rule is used to determine the direction of the current in a conductor due to the motional EMF. Okay. So this is the magnetic field, uniform magnetic field perpendicular to the plane of the board or plane of the paper, in which a conductor PQ of length L, moves perpendicular to the magnetic field. As a result, the charge at P will experience a Lorentz force. A positive charge at P will experience a Lorentz force towards the end Q. Then the EMF is given by work done per unit charge. That is what we have derived in the previous class. Now, the direction of the induced current is given by the Fleming's right hand rule. So I am talking about the Fleming's right hand rule. So the Fleming's right hand rule is used to determine the direction of the induced EMF or induced current due to the motion of a conductor in a uniform magnetic field. So according to the Fleming's right hand rule, the right hand is stretched such that the first three fingers are perpendicular to each other. And the first finger points in the direction of the magnetic field. According to Fleming's right hand rule, the first three fingers of the right hand are stretched perpendicular to each other, and the first finger points in the direction of the magnetic field. The first finger points in the direction of the magnetic field, and the thumb points in the direction of the motion of the conductor. The thumb gives the direction of motion of the conductor. Then the middle finger gives the direction of the current, direction of the induced current. So here once again, according to the Fleming's right hand rule, the first three fingers are stretched perpendicular to each other. Then the first finger points in the direction of the magnetic field. The thumb points in the direction of motion of the conductor. And the middle finger points in the direction of the current. That is, so in this system, that is yesterday in the previous class we have derived. So the magnetic field is into the plane of the board. The magnetic field is into the plane of the paper or into the plane of the board. So this first finger gives the direction of the magnetic field, and conductor is moving towards left side. So thumb gives the direction of motion of the conductor. Then the middle finger gives the direction of motion of the induced current. So induced current will be from P to Q. Understood? According to the Fleming's right hand rule. Okay. If the conductor moves instead of in this direction, if the magnetic field is there, so on both the sides, so let us consider. Then if the conductor moves in this direction, towards the right, then the induced current, the direction of the magnetic field is into the plane of the board, and the conductor is moving in this direction. Then the middle finger gives the direction of induced current. So the direction of induced current will be from Q to P. Understood the concept? This is called Fleming's right hand rule. Understood? So Fleming's right hand rule is used to find the direction of the induced current direction of the induced current. Okay. So this is also called as dynamo rule. It is also called as dynamo rule or generator rule. It is also called as generator rule. Okay. So in the previous class, we have derived the expression for this motional EMF. Okay. Similarly, same way. So that is a uniform magnetic field is there. In this uniform magnetic field, there is a conductor of length L. A conductor of length L. If the conductor moves perpendicular to the magnetic field, then a charge will experience a force, then induced EMF you will get. Okay. So now, if the conductor rotates, if the conductor PQ, let us say conductor is like this, PQ, this is P and this is Q. Okay. If the conductor moves upward or downward, then we can find once again the same formula, and by using this one you can tell the direction of the current. So that is this is the direction of the magnetic field, and this is the direction of the motion of the conductor. If conductor moves like this, then this will be the direction of current. The direction of current will be from Q to P. Similarly, if the conductor moves, so downward instead of upward, if the conductor moves downward, so then the current will flows, the induced current will flows from P to Q. Okay. So what if the point P is fixed, the end of the conductor point P is fixed, and Q rotates in the magnetic field, that is the conductor is rotated in a circular path, then what will be the motional EMF? So that is motional EMF due to rotation of conductor, in a magnetic field, in uniform magnetic field. So that is we have to find. So if conductor of length L, that is conductor of length L is placed in a uniform magnetic field, the magnetic field is perpendicular to the length of the conductor and into the plane of the board. So now if the conductor moves, that is conductor rotates, then what will be the induced EMF? First find out the induced EMF, after that direction. Okay. So let us consider a conductor of length L placed in a uniform magnetic field of magnitude B, perpendicular. The magnetic field is perpendicular to the plane of the board and perpendicular to the length of the conductor. So now the conductor, if conductor covers a angle alpha, if conductor covers a angle alpha in a time delta t, if the conductor moves or rotates by an angle alpha, then area swept by the conductor, PQ, conductor PQ is given by A is equal to, that is 1 by 2 length of the conductor L into this distance, you can write it as L alpha into L alpha. So it is A is equal to 1 by 2 L square alpha. This is area swept by the conductor. And now flux linked is given by flux linked with the conductor, that is flux linked is phi is equal to BA, that is formula already we know. So phi is equal to BA cos theta. Phi is equal to BA cos theta, and theta is the angle between the normal of area, that is area vector. Theta is the angle between the area vector and magnetic field. Theta is the angle between the area vector and magnetic field. Magnetic field is into the plane of the paper, and let us take the area vector is also into the plane of the paper. Then theta is equal to 0 degree. So you will get BA, cos of 0 degree is 1. So that is cos of 0 degree. Then phi is equal to B into A. So now area swept by the conductor, substitute that A here. So phi is equal to B into area swept is 1 by 2 L square into alpha. So this is the flux linked with the conductor when the conductor rotates in the magnetic field. So now the induced EMF is given by the induced EMF is given by E is equal to, magnitude of induced EMF is given by E is equal to d phi by dt. We know that the magnitude of the induced EMF is given by E is equal to d phi by dt. So therefore E is equal to d by dt of phi. Phi is, we got already, B 1 by 2 L square into alpha. So therefore, so E is equal to B. Magnetic field is uniform. Uniform magnetic field, taken it outside. 1 by 2 is a constant, taken it outside. Magnetic field is uniform and length of the conductor is also constant, take it outside. So it is d alpha divided by dt. That is alpha changes. So as the conductor rotates, the value of alpha will changes with respect to time. So d alpha by dt is nothing but it is rate of change of angle, rate of change of angular displacement. So this is nothing but angular displacement only. So rate of change of angular displacement is gives angular velocity. So E is equal to 1 by 2 B L square, B L square omega. So this is the expression for the magnitude of the induced EMF, magnitude of the induced EMF due to the rotation of conductor in a magnetic field. The magnitude of the induced EMF due to the rotation of the conductor in a magnetic field is given by E is equal to 1 by 2 B L square omega, where B is the magnitude of the where B is the magnetic field. B is the magnetic field, strength of magnetic field. L is the length of the conductor. L is the length of the conductor. Omega is angular velocity of the conductor. Omega is angular velocity of the conductor. So now the conductor is rotating in this direction, that is which direction? Anti-clockwise direction. When the conductor is rotating in anti-clockwise direction. Now let us find the direction. This is induced EMF, magnitude of induced EMF. Now how to find the direction? Same, you can use once again the Fleming's right hand rule. According to Fleming's right hand rule, the direction of the magnetic field is given by the first finger, that is first finger into the plane of the board. The direction of the magnetic field is given by first finger into the plane of the board, and the motion of the conductor is given by the thumb. The motion of the conductor is like this, that is upward. So then the direction of the current is given by the middle finger. So the current flows from Q to P. When the conductor rotates in anti-clockwise direction, when the conductor rotates in anti-clockwise direction, the current flows from Q to P. If the conductor rotates in clockwise direction, if the conductor rotates in a clockwise direction, that is the induced current will be from P to Q. The induced current will be from P to Q. Understood? So this is the magnitude and the direction of motional EMF due to the rotation of the conductor. Understood? Okay. So now this is about motional EMF. Okay. Next concept, energy consideration in motional EMF. Energy consideration in motional EMF. Okay, let us discuss about motional EMF due to the rotation of conductor is over. So energy consideration in a motional EMF. Okay, this is tricky. Okay, so consider a conductor of length L. Consider a conductor of length L placed in a uniform magnetic field B. Placed in a uniform magnetic field B. So this is conductor of length L placed in a uniform magnetic field B, placed in a uniform magnetic field B. The magnetic field is perpendicular to the plane of the paper into the plane of the paper, perpendicular to the plane of the paper and into the paper. So let us consider that this conductor moves on a rectangular frame. Rectangular frame. Let us consider that this conductor moves on a rectangular frame of zero resistance. This rectangular frame does not have any resistance. A rectangular frame is there. On this rectangular frame, this conductor moves. So PQ of length L moves in this direction on this rectangular frame. Okay. So then the induced EMF in the conductor, that is the induced EMF in the conductor, that is motional EMF, is given by BLV. The motional EMF is given by BLV. If R is the resistance of the rod PQ, if R is the resistance of the rod, then induced current in the rod PQ, induced current in a rod PQ is, so I is equal to EMF, that is induced EMF divided by resistance, if R is the resistance of the rod. So if capital R is resistance of rod, then induced current in a rod PQ is I is equal to E divided by R, that is I is equal to BLV divided by R. Say it as equation number 1. So this is induced current, and the direction of the induced current will be from P to Q, as we have already studied. So now the conductor carrying current placed in a magnetic field. A conductor carrying current placed in a magnetic field will experience a force, which we have already studied in the previous chapter, mechanical effect of electric current. In the previous chapter only we have studied a current carrying conductor placed in a magnetic field will experience a force, and the force experienced by, that is Lorentz force experienced by the conductor. The Lorentz force experienced by the conductor is given by F is equal to BIL sin theta. That is the formula for Lorentz force. So therefore F is equal to B, that is magnitude of the EMF, magnitude of the magnetic field, strength of the magnetic field. I, that is current flowing through the conductor, that is BLV divided by R. And L is the length of the conductor into sin theta. So theta is the angle between the velocity of the conductor and magnetic field. So from Lorentz force, theta is the angle between the velocity of the conductor and magnetic field, and magnetic field is into the plane of the conductor, and velocity of the conductor is in this direction, that is 90 degree. So sin of 90 degree is 1. So therefore, so the Lorentz force acting on the conductor is given by F is equal to B square L square into V divided by R. And the direction of this Lorentz force is outward, that is against the motion of the conductor. The direction of this Lorentz force is outward, that is against the motion of the conductor. As a result, to maintain the motion of the conductor, an external force has to be applied. See here, the Lorentz force acting on the conductor carrying current placed in a magnetic field is given by F is equal to B square L square V divided by R, that is F is equal to BIL sin theta. Using that you got this one, and this force acts outward, that is in a direction opposite to the direction of motion of the conductor. As a result, to maintain the motion of the conductor, to maintain the uniform motion of the conductor, an external force of same magnitude, has to be applied. So therefore, the power spent or the power applied by external force, external force is given by P is equal to F into V. So therefore, that is P is equal to F, that is force, that is B square L square V, divided by R into V. So you will get power P is equal to B square L square V square divided by R. This is power spent or power applied by the external force to maintain the motion of the conductor, to maintain the uniform motion of the conductor in the magnetic field. And this power applied is converted into energy. This power applied is converted into energy. That is according to the Joule's law. That is the power dissipated according to the Joule's law. The power dissipated in the coil or in the conductor is given by P is equal to I square into R. According to the Joule's law, the power dissipated in the conductor. So this is power dissipated in the conductor. I will write it as Pj. According to the Joule's law, P is equal to I square into R. So therefore, P is equal to I, that is current flowing through the conductor, BLV divided by R. This BLV divided by R whole square into R. That is Pj is equal to B square L square V square divided by, so divided by R square and R cancel. So Pj, that is power dissipated according to the Joule's law, is given by Pj is equal to B square L square V square divided by R. Now compare these two equations. Comparing these two equations, so we found that both the equations are same. That is, the mechanical energy spent to maintain the uniform motion of the conductor in the magnetic field. The mechanical energy spent to maintain the uniform motion of the rod PQ in the magnetic field is converted into induced EMF. Is first converted into induced EMF, then it is converted into heat energy according to the Joule's law. Understood? According to the Joule's law. That is, it is in accordance with the law of conservation of energy. It is in accordance with the law of conservation of energy. I will tell once again. Understood once again. We have derived the motional EMF. In the previous class, we have derived the motional EMF. It is a conductor PQ placed in a uniform magnetic field moving with a velocity v. So the motional EMF is given by E is equal to BLV. Okay. So if R is the resistance of the conductor, if R is the resistance of the conductor rod, then induced current in the conductor is given by I is equal to E divided by R. That is, induced current I is equal to BLV divided by R. Call that as equation number 1. So now a current carrying conductor placed in a magnetic field. A current carrying conductor placed in a magnetic field will experience as a force, that is Lorentz force, and it is given by F is equal to BIL sin theta. So that F being magnetic field, so I, that is induced current, BLV divided by R, L length of the conductor, and theta is angle between the motion velocity of the conductor and magnetic field, so sine of 90 degree. So I will get this is the force, and this Lorentz force acts in a direction outward, that is acts in a direction opposite to the direction of motion of the conductor. This force acts in a direction opposite to the direction of motion of the conductor. As a result, to maintain the uniform motion of the conductor, we have to apply an external force. To maintain the uniform motion of the conductor in the magnetic field, we have to apply an external force. So hence, power applied by external force or power used because of external force is given by P is equal to F into V. External force applied must be same as the Lorentz force. So that is P is equal to F into V, P is equal to F, that is B square L square V divided by R into V. So B square L square V square divided by R. So this is the mechanical energy spent, that is energy spent per second, that is work done per second, to energy spent per second to maintain the motion of the conductor, to maintain the uniform motion of the conductor in the magnetic field. And now according to the Joule's law, the power dissipated, the power generated in the conductor or rod is given by, so Pj, that is power generated in the rod, is given by I square into R. So that is I is induced current, so it is BLV divided by R squared into R. So it is, on simplification you will get same formula. So from these two formula we observe that this is a formula number 2 and equation 2 and 3 comes out to be same. So thus we understand that the mechanical energy spent to maintain the uniform motion of the conductor, the mechanical energy spent to maintain the uniform motion of the conductor is first converted into induced EMF, then into heat energy according to the Joule's law. Understood? So thus it is in accordance with law of conservation of energy. So this all the things, electromagnetic induction is in accordance with law of conservation of energy, that is energy consideration in motional EMF. Understood? So understand this concept properly. Okay. Next heading. So these all are important concepts that you have to understand. So next concept, so relation between relation between induced charge and magnetic flux or change in magnetic flux. Relation between induced charge and change in magnetic flux. This is simple but important to be understood. Relation between induced charge and change in magnetic flux. So according to the Fleming's law, that is according to the Faraday's law, or according to the laws of electromagnetic induction, the magnitude of the induced EMF is given by E is equal to d phi by dt. The magnitude of the induced EMF is given by E is equal to d phi by dt. If R is the resistance of the conductor or rod, then the induced current is given by I is equal to E divided by R, that is d phi by R into dt. And now the induced current can be written as in terms of induced charge, that is dq divided by dt, because we know that I is equal to dq by dt. You know this formula, I is equal to dq by dt. So instead of induced current, induced charge per unit time, that is dq by dt is equal to d phi divided by R dt, where dq is induced charge induced in a time interval dt, dt. So therefore, from this we find that dq is equal to d phi divided by R, that is the induced charge in the rod in a time dt is given by the induced charge in the rod in a time dt is given by dq is equal to net change in the magnetic field, net change in magnetic flux divided by resistance of the conductor, Thus the induced charge does not depends upon the time interval, time taken for the flux to change. The induced charge depends only on the net change in the magnetic field and does not depends on the time taken to change the magnetic flux. Understand properly. The induced charge does not depends upon the time taken to change the magnetic flux. It depends only on the net change in the magnetic flux and also depends upon the resistance of the conductor. That means the induced charge does not depends upon the rate of change of magnetic flux. The induced charge does not depends upon the rate of change of magnetic flux, whereas the induced EMF depends upon the rate of change of magnetic flux. The induced EMF depends upon the rate of change of magnetic flux, whereas induced charge only depends upon the net change in the magnetic flux and also depends upon the resistance. Understood? Whereas induced EMF depends on the rate of change of magnetic flux and induced EMF does not depends upon the resistance of the conductor. The induced EMF does not depends upon the resistance of the conductor. The induced EMF depends only on the rate of change of magnetic flux. Whereas induced charge does not depends upon the rate of change of magnetic flux. It depends only on the net change in the magnetic flux, also on the resistance. Understood? So this is the relation between induced charge and change in a magnetic flux. Understand this properly. Okay. Okay, now let us solve simple numerical related to this motional EMF. A simple numerical related to motional EMF. Take the pen and paper, pause the video, take the pen and paper so that you can write the numerical. I will dictate the question, you have to write the numerical. As you know, in the previous chapter also we had it the same way. That is how I will take the class. Okay. Hope you have taken the pen and paper and writing. Okay. So first numerical. Write down the question. I'll explain the question. Write down. A wheel with metallic spokes. A wheel with metallic spokes, each 0.5 meter long. A wheel with metallic spokes. A wheel with metallic spokes. With metallic spokes, each 0.5 meter long, is rotated with a speed of 120 revolution per minute. With a speed of 120 revolution per minute. A wheel with metallic spokes, each 0.5 meter long, is rotated with a speed of 120 revolution per minute in a plane normal to the horizontal component. In a plane normal to the horizontal component of Earth's magnetic field. In a plane normal to the horizontal component of Earth's magnetic field. In a plane normal to the horizontal component of Earth's magnetic field BH at a place Q list off. At a place Q list off. So here this is complete one sentence. I'll read once again. A wheel with metallic spokes, each 0.5 meter long, is rotated with a speed of 120 revolution per minute in a plane normal to the horizontal component of Earth's magnetic field BH at a place Q list off. If BH is equal to 0.4 Gauss, if BH is equal to 0.4 Gauss, capital G, at the place, if BH is equal to 0.4 Gauss at the place, come on. What is the induced EMF? What is the induced EMF? What is the induced EMF? Between the axle and the rim of the wheel. What is the induced EMF? Between the axle. What is the induced EMF? Between the axle and the rim of the wheel. What is the induced EMF between the axle and the rim of the wheel? Question mark. Question mark. Question mark. Note that 1 G is equal to, that is 1 Gauss is equal to 10 to the power minus 4 Tesla. Okay. See here. So what they have given? A wheel with metallic spokes, each 0.5 meter long, is rotated with a speed 120 revolution per minute in a plane normal to the horizontal component of Earth's magnetic field BH at a place. Okay. So now here given. So what is the given data? So the length of the each spoke is given as 0.5 meter. L is equal to 0.5 meter. Rotated with a speed, that is frequency of revolution. F is equal to 120 revolution per minute they have given, and we have to convert into revolution per second. It is 120 revolution per 1 minute. 1 minute means how many seconds? 60 seconds. So this becomes revolution per second. So therefore F is equal to 2 RPS. You can write F is equal to 2 RPS. And BH, that is magnetic field. Magnetic field at that place is 0.4 Gauss. That means 0.4 into 10 to the power minus 4 Tesla. Right? And now the induced EMF. So we know that the induced EMF is given by E is equal to 1 by 2 B L square omega. E is equal to 1 by 2 B L square omega, where omega is angular velocity. So since omega is equal to 2 pi f, you know all this. So omega is equal to 2 pi f. So therefore E is equal to 1 by 2 B L square 2 pi f. So this will becomes E is equal to B L square. B L square 2 cancel, so pi f, B L square pi f. So E is equal to B, magnetic field. Magnetic field is 0.4 into 10 to the power minus 4 L square, that is length 0.5 square, pi is 3.142, and F, that is frequency of revolution, is 2 revolution per second. So therefore induced EMF. So do the calculation, you will get the answer. So the answer comes out to be 6.28 into 10 to the power minus 5 volt. 6.28 into 10 to the power minus 5 volt. So this is the induced EMF. And since all the spokes, here wheel means like this, it will be, spokes will be like this. Here, since one end of all the spokes is connected at the axle, connected at the center. One end of all the spokes is connected at the center, and another end of all the spokes are connected to the rim. So that means all these spokes are parallel to each other. All the spokes are parallel to each other. So therefore EMF will remain constant. That is the potential difference will remain constant. You know that in the parallel combination potential difference will remain constant. So that is here one end of all the spokes is connected to the axle, that is rim, that is center, and another end is connected to the rim. That means both the ends are connected between the same 2 points. That means all the spokes are parallel, they are connected parallel, hence EMF will remain same. So the number does not matter, how many spokes it may be, the EMF will be same. Okay. So now write one more homework. Okay, one more question as homework. Write down another one question. Write another question as homework. Another question you write, I will dictate, and this will be homework. Very simple question. A metallic rod 1 meter length. A metallic rod of 1 meter length is rotated with a frequency of 50 revolution per second. A metallic rod of 1 meter length is rotated with a frequency of 50 revolution per second. A metallic rod of 1 meter length is rotated with a frequency of 50 revolution per second, comma. A metallic rod of 1 meter length is rotated with a frequency of 50 revolution per second, comma, with one end hinged at the center, with one end hinged at the center and the other end at the circumference of a circular metallic ring, with one end hinged at the center and the other end at the circumference of a circular metallic ring, with one end hinged at the center and the other end at the circumference of a circular metallic ring, and the other end at the circumference of a circular metallic ring, of radius 1 meter, of radius 1 meter, comma, of radius 1 meter, comma, of radius 1 meter, comma, about an axis passing through the center, about an axis passing through the center, about an axis passing through the center and perpendicular to the plane of the ring, about an axis passing through the center and perpendicular to the plane of the ring, about an axis passing through the center and perpendicular to the plane of the ring, plane of the ring. You please stop. About an axis passing through the center and perpendicular to the plane of the ring, ring, ring. You please stop. A constant and uniform magnetic field of, a constant and uniform magnetic field of 1 Tesla, a constant and uniform magnetic field of 1 Tesla and parallel to the axis is present everywhere. A constant and uniform magnetic field of 1 Tesla and parallel to the axis is present everywhere, and parallel to the axis is present everywhere. A constant and uniform magnetic field of 1 Tesla and parallel to the axis is present everywhere. You please stop. You please stop. What is the EMF between the center and the metallic ring? What is the EMF between the center and the metallic ring? Question mark. What is the EMF between the center and the metallic ring? Question mark. Solve this on your own at the home. You can solve it, very simple. So the answer comes out to be 157 volt. The answer for this question is 157 volt. 157 volt. So try to solve this question on your own. Okay. So in the next class we'll solve some more numericals and some next another concept if possible.